Hello everyone. So in the last video we looked at one application of integrals, which was to find areas of enclosed regions. In this video we're going to look at another application, which is to find something called arc length, which is really just the length of a curve between 2 points. So as you see here, we have a black line right here which represents the curve f of x, and this variable called s right here, that represents the actual length of that curve. So let's pretend this curve was like a string or something, and we stretched out and measure it. That's how much length of string would be taken up by this particular curve. And this is a very minor portion of the AP curriculum, so we're just going to do a very short video of it. It's also extremely formula based. There's just this one integral formula that we use to find it, but we'll go over the derivation here. So the derivation is actually pretty simple. I can even show you in a 5 to 6 minute video. Yeah, good voice crack right there. Okay, so yeah, like I said, 5 to 6 minute video, which I'll show you right now. So let's pretend we want to find the length of this curve f of x between x equals a and x equals b, remembering that that length of the curve represents this thing called s. So remember, an integral gives us a net change, and it gives us a net change by doing this thing called a Riemann sum, where we're adding up a bunch of teeny tiny changes, and over the long run, over some interval, all those teeny tiny changes, their summation results in some kind of net change. So in this case, let's look at how we would look at or approximate a teeny arc length. So in this case, remember, when we put the variable d in front of something in calculus, that means tiny change. So in this case, it's saying, okay, a tiny change in an arc length, if we zoom in really close to a function, all functions look linear when you get basically small enough in a small enough scale. So we can approximate the arc length by this straight red line. And this straight red line has x and y components of a tiny change in x, dx, and a tiny change in y, dy, and these make up a right triangle. So we can basically just apply the Pythagorean theorem, okay? We have that the hypotenuse squared is equal to the sum of the square of the two sides. Now what we can do now is apply a little trick and just divide everything by dx squared, and then we get this equation down here, and it starts to look like things are a little bit more familiar. So let's see where this goes. So, well, okay, let's write ds dx all by itself. That means we take the square root of both sides. So we'll take a big square root right here. Well, dx over dx, that's just 1. So we get 1 here. And, well, dy dx, well, that's just another way of saying f prime of x. So this will be 1 plus f prime of x squared. Okay? Now, if we multiply both sides by dx, like if I multiply this by dx up here and this by dx right here, notice these two dx's cancel out, and I'm left with ds equals square root of 1 plus f prime of x dx. So what does that look like when we see a dx come after something or a d something after something anywhere? It looks kind of like an integral. So what we can do is we can integrate both sides, and lo and behold, if we integrate, let's say, from some point A to some point B, some point A to some point B, what we're going to end up getting is that our arc length essentially from A to B is going to be the total sum of these individual ds's between A to B. So that's going to give us our total arc length right there, and that will just be equal to the integral from A to B of the square root of 1 plus f prime of x squared, okay, dx. So this is it. I said it was a formulaic approach, and this is the formula which we use. I'm just going to erase this to write it a little bit neater. So we essentially have arc length is equal to this. And because of this f prime of x squared that goes in here, typically you see these questions, they either show up as just show the integral expression but don't evaluate the integral, or they show up as something in the calculator section of the AP exam where you can just use f and I and t. But we will go through and do a non-calculator version of this as a problem on the next page. All right, so just get this square formula written down because you're going to need it. and then answer this question with that formula. Pause the video, give it a shot. All right, so if you guys do this, you know that if we want to find the arc length, that's going to be the integral over the interval. The interval in this case is 0 to 1 of square root of 1 plus dy dx squared dx, okay? So the first thing we got to find is dy dx. All right, go back to integrals. Power rule. All right, so what's the integral of this? Okay, well, the power is to the 3/2, so that comes down to the front. The constant stays out there. It just hangs out. That's what constants do. So we'll get this times 3/2 times x, and then 3/2 minus 1 is 1/2. The derivative of a constant is just 0, so that's nothing. So if we go to simplify this thing, we end up with just 2 square root of 2, actually 2 square root of 2x, because x is to the 1/2 power. All right? So now the next thing is to find dy squared, or dy dx squared. Well, dy dx squared is just going to be squaring this thing, which will give us 4 times 2x, or 8x. That's why I said this one was nice. It's kind of a non-calculator one. It comes out to be nice. So if we plug all this into that integral, we get s is equal to the integral from 0 to 1 of the square root of 1 minus 8x dx. And how do we solve an integral like this by hand without a calculator? All right, why don't you actually pause the video if you haven't done this section yet and see if you can think back, dust out those cobwebs, and see how you would solve an integral like this. Okay, if you get in a shot, we would find this integral by using a u substitution. So let's say u is equal to 1. Actually, why did I put minus? That's supposed to be a plus. Sorry about that. So 1 plus 8x. All right. So then du is 8 dx, or 1/8 du is dx. We can also substitute out or swap our limits of integration. So u of 0 is now going to be 1 plus 8 times 0, which is 1. And u of 1 will be 9. So this becomes the integral of 1 to 9 of square root of u. Actually, I'll put the 1/8 out front here. 1/8 square root of u du, which would give us 1/8 2/3 u to the 3/2 from 1 to 9. All right. So if we evaluate this, this will be 1/8 times 2. Actually, let's just simplify 1/8 times 2/3. That'll be 2 24ths, or 1/12. So 1/12, 9 raised to the 3/2 minus 1/12, 1 raised to the 3/2. All right. So remember, 9 to the 3/2. Let's extend the page here. 9 to the 3/2 is the same as the square root of 9 times cubed. So this will end up being 27 over 12 minus, well, that just becomes 1. So that just becomes, and that was a 12 right there, 1 over 12. That's nice. So we end up getting 26 over 12, or 13 over 6 as a final answer. So again, I didn't go into all this algebraic stuff in the last one, but I want you guys to always be practicing doing stuff without a calculator, because it's going to come in handy huge on the AP exam. Easily, and every year I've taught this course, the number one, or actually the two most common complaints of students coming out of the exam were, I wish I studied how to do things without my calculator more, and I wish I memorized the unit circle. So make sure you do those things before you get into the AP exam. We'll do some example problems on arc length when we get into the next class, so come to class ready with questions.